Hello and welcome to my video. Few days ago, I uploaded this video where I find the real solutions to the equations with multiple absolute value signs. If you haven't seen this video, I recommend to watch it first before watching this one, so please check the link in the description or on the top right corner. In that video, one of my viewers commented to ask what would be the solutions if we allow the complex numbers as well. And I thought that's a nice topic to make another video, so thank you again for the interesting suggestion. Right, so we are going to find all complex solutions to this equation. Again, for real value solutions, check my video in the description. But before we handle this equation, let us handle this first. What is the absolute value of a complex number? We can express the complex number in many ways. The most famous one is of course expressing as z equals x plus yi, where x and y are real numbers, so this x is real part and y is the imaginary part. And we can also denote this complex number on the complex plane like this. Here, the absolute value of z is given as square root of x squared plus y squared. In other words, the absolute value of the complex number z means the distance between the point z and the origin on a complex plane. Now we can express the complex number also like this. Z equals r times cosine theta plus I sine theta, where r is a positive real number and theta is from 0 to 2 pi. This is also known as the polar form. This is the expression of a complex number using the distance r and angle theta, as you can see in this complex plane. For this expression, the absolute value of z is simply given as r. Alright, so now with this established, let us move on to the next step. Here, let us think about the trick to solve the given equation. For that, let us think about the simpler case, absolute value of z equals a. With only real numbers, this simply means that z equals a or minus a. But with complex numbers, the trick becomes like this. The absolute value of z being a is equivalent to z being a times cosine theta plus I sine theta, where this theta is from 0 to 2 pi. Okay, so these are all fairly straightforward, but let us visualize these statements for a deeper understanding. For real numbers, the solutions to the equation absolute value of x equals a is either x equals a or x equals minus a, which are two numbers on the real number line. So we have these 2 points on a one-dimensional space. Now for the complex word, z satisfying this equation can have any values that can be expressed as a times cosine theta plus I sine theta, so we have infinite solutions. So this expression means that z has a fixed absolute value a, and the angle theta can have basically any values since it is given as from 0 to 2 pi. This means that z satisfying these equations is given as the circle with origin 0 as its center and absolute value a as its radius. Here, if we overlap our real solutions on this complex plane, we can see that the real solutions a and minus a are the special case of the complex solution, that is, the solutions on the real axis. So this is how the real and complex solutions are related. Now finally, let us tackle our given equation. So first, let us remove this outermost absolute value sign. Then we have this expression equals cosine theta plus I sine theta. Moving one to the right hand side, we have this term equals cosine theta plus 1 as the real part and sine theta as the imaginary part. But here, the left hand side is an absolute value of some complex number, so it is a real number. This means that the right hand side must also be the real number, so the only possible values are when this imaginary part becomes 0. That is, when theta equals 0 or theta equals pi. Therefore, the only possible values are when theta equals 0, we have 2, and when theta equals pi, we have 0. Again, let us remove the outermost absolute value sign. Then this equals, from 2, we have 2 times cosine theta plus I sine theta. And from 0, we simply have 0. Again, moving 1 to the right hand side, we have absolute to z minus 1 equals, from here, we have 2 cosine theta plus 1 plus I times 2 sine theta. And from here, we simply have 1. Again, since this left hand side is real value, so the imaginary part on the right hand side must be 0. So only theta equals 0 or theta equals pi are possible. So we have absolute value of z minus 1 equals, if theta equals 0, we have 3. If theta equals pi, we have minus 1, and then of course 1. Here, this absolute value of z minus 1 is non-negative, which means that the case that this value equals minus 1 is impossible. So we only have 3 and 1, so therefore z minus 1 equals 3 times cosine theta plus I sine theta, or cosine theta plus I sine theta. Therefore, if we move this one to the right hand side, we have z equals 3 cosine theta plus 1 plus I 3 sine theta, or cosine theta plus 1 plus I sine theta. Here, the left-hand side is no longer limited to real values, so all of these values are valid answers. Therefore, this is the complex solution to the given equation. As you can see, we now have infinite number of roots. Now, let's actually visualize these solutions on a complex plane. So we have this expression, but the best starting point is here. Absolute value of z minus 1 equals 3 or 1. And we can write down like this. Now let us take a look at this first equation. This means that on the complex plane, the distance between the 2 points z and 1 is equal to 3. And that means that the complex numbers z satisfying this equation is on the circle with center 1 and radius 3, like this. So this equation is basically the equation of this blue circle on the complex plane. And similarly, this second equation means that the complex number z satisfying this equation is on the circle with center 1 and radius 1, like this. Therefore, the plot of all the roots to this given equation are two circles with the same center 1 with two different radii. Finally, in my real solutions video, I have obtained the real solutions to the equations, which is minus 2, 0, 2, and 4. And if we plot these real solutions on the complex plane, they are at these locations. So here again, we can see that the real solutions are part of the complex solutions, but only on real axis. And that concludes this complex equation video. Thank you for watching. And please hit that like and subscribe buttons for more interesting math problems and insights. And I will see you in another video.